Here is one arrow. In this grid, you read off its coordinates 4 across, 2 up. 4, 2. That is the vector, right? Hold that thought, but watch. Lay a different grid over the exact same arrow, skewed axis, and now the very same arrow reads as 2, 0. The arrow did not move one bit, only the numbers changed. So, which list of numbers is the real vector? The answer is neither, and it changes how you see all of linear algebra. Back to episode 1.2. Every grid is built from two basis arrows, I hat, one step right, and j hat, one step up. So the coordinates 4, 2 are not the vector, they are a recipe. Go 4 I hats, then 2 j hats. Change the arrows you build from, and the recipe for the very same destination changes. The same street corner has a GPS coordinate and a nearest subway stop. Two completely different labels for one spot on the map. Neither is the real location, the corner just is. The labels only exist once you pick a system. Now choose a new pair of basis arrows, B1 and B2, pointing wherever we like. The yellow vector has not moved. How much of each do we need to reach the tip? 2 steps along B1 lands us exactly there, no B2 at all. So in this basis, the same arrow is just 2, 0. Here is the machine that does the translating. Stack your new basis arrows as the columns of a matrix. Call it B. B takes coordinates written in the new basis and gives you back the standard ones. And B inverse runs it the other way. Feed it standard coordinates. Get the new ones out. 2 directions, 1 matrix and its inverse. That is all a change of basis is. 20 degrees Celsius and 68 degrees Fahrenheit are the same warmth. The thermometer did not change, only the scale did. Converting between them is a tiny formula, run one way or the other. B and B inverse are that formula for vectors. But here is where it earns its keep and why every AI quietly does this. Now the move that unlocks the rest of the season. Suppose you want to apply a transform, but it is ugly in the standard grid. Do this. Translate your vector into the friendlier basis B inverse. Do the transform there, A. Then translate the answer back, B. Read it right to left, B inverse A, B. Translate, add, translate back. This sandwich is called a similarity transform, and once you see it everywhere in machine learning. Here is the payoff. Take a transform and apply it in the ordinary grid. Everything twists, lines rotate, the whole plane shears. Messy? Hard to read. But now measure the same transform in the basis of these two special directions. Watch what the warp becomes. Pure stretches. No rotation at all. One direction grows by 3. The other stays put. It never leaves its own line. In this basis, the messy matrix becomes a clean diagonal. Just 2 stretch factors. That magic basis has a name, the eigenbasis, and it is the whole next episode. It is also what PCA finds in your data, and what every attention head learns, the coordinates where the problem is finally simple. A few lines and you can feel it. B. Inverse times a vector re-expresses it in the new basis. And if you use a matrix's own eigenvectors as the basis, that sandwich V inverse AV comes out diagonal. The full notebook is in the description. The map so far. And today a hinge, a vector's coordinates are a choice of basis, and switching basis is a matrix B and its inverse. You are here. What it buys you. A vector's numbers are only its shadow in one chosen basis. B and B inverse translate between them. And the reason AI cares, PCA, and attention heads are each just a learned change of basis, a better set of coordinates. Next stop, the special directions, a matrix only stretches and never rotates, the eigenvectors, and the magic basis where every warp becomes simple. Next, the special directions, a matrix only stretches, never rotates, the eigenvectors, and the magic basis where every warp becomes simple. Thanks for watching and keep exploring. Next time, eigenvectors, the axes that don't rotate. Please like and subscribe ThirdEye Labs if you enjoyed this video, and let me know in the comments.